I will begin. Dear Heavenly Father, we thank you for this afternoon. Thank you for these students. Pray you would be with us today. Help us to glorify you, what we do, and just pray you give understanding as we look at the proof of Maskey's theorem, Lord. In your name I pray. Amen. So I guess first I owe you guys an example or two. Let's see here. We are in section 18.1. Wow, right? It's been a long journey. Let's see here, 18.1 of, we skipped the hard chapter, by the way, like between the Galois theory and the, where we are, there's a couple of chapters on harder things. There's like an 80-page arc in this book that starts what's called algebraic geometry. You guys study level curves, right? Like Calculus 3, algebraic geometry is like that, but more. It's all about studying curves by their equations in some sense or another. I'm sure algebraic geometers would not like me saying that. Let's see here. Now, so I have examples here of some representations of groups. So let's see if I can't write a few up here. I'll skip example 1. It's too silly. Example 2 is kind of nice. Example 2, we have V is the, what is this thing? You guys remember? Right? It's a group ring. He says, consider this, consider this ring as a left module over itself. All right. He says, V affords a representation of G equal to, what's that mean, V affords? It has, exactly, it has a representation of that degree. I mean, that was the language he introduced on the last page. Let's see here, So we'll take the elements of G as a basis for V. Each G and G permutes these basis elements under the left regular permutation representation. So what we're about to show is the left regular permutation representation. Here it is, G dot GI is equal to GGI. Okay. He says, with respect to this basis of V, the matrix of the group element G has a 1 in row I and column J if G times Gj is GI, and 0 in all other positions. This linear or matrix representation is called the regular representation of G. Note that each non-identity element of G induces a non-identity permutation on the basis of V. So the regular representation is always faithful. Let's see here. That's great. Let's actually look at this thing for a specific group just to be a little bit more concrete. I mean, so you guys give me a group of small order that we can do this on. Z7. Z7. Fine. I'll let you have your 7. I'll let you have your 7 just this once. All right. So this is an additive group. Actually, let's 7 equal 2.
Okay, I gotta be honest. I really didn't even think of 7. I just said Z7 because it was a small prime number. I realized you're seriously didn't even think of that.
Well, we're talking about groups here. I mean, you could pick any Z. Like, we could do Z3 or anything.
It just seemed too Z3, Z5 seemed I'm sorry. I really didn't need to pick Z7.
So I don't know. I just prefer the multiplicative notation here for whatever reason. Right. So we could look at this as the cyclic group of order 7 with generator A, right? I mean, if you want me to be more explicit, you could even let A equal to e to the 2 pi I over 7, right? But that's not necessary if you like. Whatever. We don't even need that. So what are the rules here? So let's see here. So we've got what? So let's see here. A times, I'm trying to think how this goes. A times, I mean, of course, the, I need a notation. I'm sorry, guys. So let's say phi of, goodness gracious. I'll use a phi sub, let's say phi sub g of x is equal to what? Right, gx for all x in g, right? Fine. So, for example, let's see here. We have phi, let's look at a specific one. Let's look at a squared. Maybe I should just look at a. Phi of a. So phi a of 1 is a, right? Phi a of a is what? Thanks, Jess. This example is entirely as long as it needs to be. It's too late. It's too late. You started it. See, so anyway, the pattern's clear enough. Oh, I'm sorry. What is 8 to the 7th? It's 1 again, right? So if you look at so if we take this as the basis for the group ring, I guess we're working over the reals. So so V equals to RG, right? And I'm supposing that Fiji is a linear transformation from V to V, right? I want to look at its matrix, actually, because I think it's fun. So like the matrix of phi of A is what? I'm identifying V as R7, if you don't mind, to be explicit. Which is to say I'm taking 1 to be E1, I'm taking A to be E2, A squared is E3, A cubed is E4. I mean, this is E1, E2, E3, E4, E5, E6, E7, right? So what's the first column in the standard matrix of phi A? And then how many zeros? 1, 2, 3, 4, 5. Thanks again, Jess. And then this E2 is... Are you? Let's see here. Doesn't seem like... I don't think you guys have really learned the lesson of not interjecting 7 comments into my lectures. I'm only happy that it's graduating with you, and then you're not passing it down to the next generation of students. No, you will not do that. You will not do that. I can change grades. It's very easy. All I have to do is email the registrar, and they will change a grade. They don't even question it. They're just like, okay, clerical error, good deal. That A you got in calculus can become a C, just like that. I can slip. Who did you take calculus with?
You don't need to know.
But I can figure it out. Oh, Kester can't be bought. Man, Kester can't be bought. Curses. So this is a matrix representation, right, of this. This is but this is kind of cool. This gives you a matrix whose, which with the property that it's going to, if you multiply it by itself 7 times, it'll go back to the identity matrix, but it won't do so before then, right? It is a, I guess that's idempotent order 7 matrix, degree 7, I should probably say. I don't know. Now, so like phi of a squared, if you want, I mean, I don't know, whatever you think is easier. What do you think is easier? Phi of a squared is equal to phi of a times phi of a. I mean, that's a property of the homomorphism, so we can multiply this by itself and come up with a matrix of that. I mean, is that faster?
It smooths everything down.
Right. And then, like that. How many? I had too many zeros. All right. Sorry, it's ugly. So these I got switcherooed. Okay. That's really cool. I can almost visualize why it is that the 7th power happens, right? Because it like,
Yeah, it pushes it through.
yeah, it's like Pac-Man, right? It's like, and then goes back to the other side, and eventually this one gets pushed all the way over to there, and then it becomes the identity matrix. That is so cool. Anyway, yeah. So there you go. There's what's actually behind the scenes there of example 2. That's kind of cool. Let's see here. I'll do example 7. I think it's interesting. I mean, all of the examples are interesting. I should get to Maskey's theorem here before too long. Oh, exactly. Actually, example 8 is one I like. So here I guess I can do 7 and 8. So 7, he talks about the quaternionic 8 group, right? The quaternionic 8 group is basically just formed by the versors. So it's I and J, such that here's generators and relations. I and J are the generators. The relations are I to the 4th equals J to the 4th equals 1. And what else? I squared equals J squared. And I inverse Ji equal to, I inverse Ji equal to, good grief, J inverse. Not personally how I think about the quaternion 8 group, actually. But he points out that you can get a representation on 2 by 2 complex matrices for this thing, and I think it's just interesting to write it down. The representation of the quaternion 8 group in terms of 2 by 2 complex matrices looks like the following. That's funny. So he's like phi of I. He puts the square root of -1 here. Just because he doesn't, I mean, why is he doing that? Right, he doesn't want you to think that they're the same I. I mean, this is the I in the quaternion 8 group. This is the I in the complex numbers. But, I don't know. I don't know if I can suffer this level of notational guilt. Let's see here. Phi of J. Like, I'm going to use I in both places, and I hope the students can deal, because otherwise I'd go nuts. 0, -1, 1, 0. These matrices, basically, I mean, I understand the notation, but
You do
what's that? I primes. Sure. So if we take phi of I, phi of j, we should get this thing called k, right? I mean, the quaternion group you can also look at as ijk, such that I squared equals to j squared equals to k squared equals to -1, and ij equals to k, jk equals to I, ki equals to j, etc. K here is ij in that generator's relations presentation of the quaternion 8 group. I prefer to work with ijk because it's more natural, even though it's not logically. I mean, the nice thing about presenting it in terms of generator being ij is that when you look at the representation, all you got to generate a representation. Okay, so here's the thing. If we have a group which is generated by elements, right? To describe the representation, it suffices to describe the matrices which represent the generators. Because then, once you have those, matrix multiplication takes the rest, takes over, right? Like in some sense, once I tell you this matrix here is, this is a generator of the representation of the cyclic group of order 7. Once you know that, you can create the rest of the representation by powering this thing, right? Because a cyclic group is obtained by powering. Now, this is a little bit more different, a little bit different. This is obtained by multiplying the generators and powering. I mean, there's a little bit more involved, but the group generation process is more interesting. But still, once I've provided this and this, I've provided everything. But on the flip side, if you multiply these two representations, that gives you what, quote unquote, k is, right? So this would be, k would be product of these two guys, which would be what? 0 minus the square root of -1. I'll suffer his notation just a second longer. Minus the square root of -1. 0, right? So in other words, you could look at Q8. Here's a different way you could look at Q8. I'll call it Q8 tilde. You could look at it as the set I, 0, 0, minus I, 0, minus 1, 1, 0, and 0, minus I, minus I. If you look at these three matrices, you could generate Q8 by those in the sense of take products, powers of these things. I think you get everything, right? Do I have to throw in minuses? I don't know. I definitely know this. If I throw in the identity, right? If I look at the identity matrix times the reals plus, I think this is true, I0. I mean, you might have to check me on this one. I conjecture that this, what I'm writing down, that this direct sum is in fact a set of 2 by 2 complex matrices, which gives you a representation of the quaternions as an algebra. So the quaternions, right, are bigger than Q8. Q8 has 8 things in it. It's a finite group, right? Quaternions, on the other hand, are things of the form what? Like A, well, let me do time space. So T plus Xi plus Yj plus Zk, right? T, X, Y, Z, real numbers. So the quaternions is a 4-dimensional real algebra. Inside the quaternions, you can find Q8, right? It's a, I believe it's a subgroup of the group of units, right? How big is the group of units for the quaternions? Oh, I'm sorry. Oh, that's very big. Yeah, this is a skew field. Everything that's not 0 has a multiplicative inverse, right? So the group of units is just non-zero quaternions. Here's a more interesting one. What are the group of quaternions If you look at the quaternions, the other thing that's interesting about the quaternions, of course, is you have this property, right? If I have Q and W, these are two quaternions. There's a there's a quaternionic conjugation that satisfies. Oh man, I forget. Oh, here's what I don't remember is if the conjugation flips the order or not. Do you guys know? I'm not sure. There are two paths we could go down here. It either does this or it does this, and I don't remember. And quaternionic multiplication is not commutative, so I just don't remember. Anyway, whichever one it does, if you take the length of a quaternion is actually, you can define it to be the square root of q bar. And that is exactly what you would think it would be. Like for this element, it would be the square root of t squared plus x squared plus y squared plus z squared, right? So quaternions are pretty neat. But if you think about that, then you can form a subgroup of quaternions, right? If you take the quaternions of unit length, the product of any two such quaternions is again such a quaternion because of this multiplicative conjugation, right? And so like this will say that the length of the product is the product of the length. So if you have quaternions of unit length, then the product of two quaternions of unit length is another quaternion of unit length. And you can also prove that the length of the inverse is the same. I mean, a formula for the inverse of a quaternion is just this. So if Q has unit length, then the length of 1 over Q is the length of this, which is the length of Q bar divided by the length of Q bar, which is the length of Q bar divided by the length squared, which is 1 over 1, which is 1. So it's closed into inverse. Anyway, so what I'm trying to tell you is there's this, by the way, if you look at, this is what's often called S3, Q and H, such that the length of Q equals to 1. The reason I say S3, if you take this and equal to 1, what you're looking at is the hypersphere in 4 dimensions. So quaternions give you a natural multiplication on the hypersphere in 4 dimensions, S3. This is very special and something that's implications really only been appreciated by mathematicians in the last like half century or so. People like Robert Bryant have used these kinds of observations to do things in recent mathematics. But anyway, and Milner too, I think, plays with these toys. But my point to you is that Q8 is actually a subgroup of this thing, right? In the multiplicative sense, it's actually, I think, a subgroup. You multiply those things, you get back into it. But anyway, my other point here, what I'm trying to get to, is that this gives you another representation of the quaternions, the representation of the quaternions as 2 by 2 complex matrices, basically of the form, how does it go? A plus, let me see if I can do this, A plus BI, and then I've got another A down here, and minus BI, like that. Let's see here, what else do I got? That's it for those guys. Then over here I've got, like minus C, minus ID, and then C minus ID. So these sorts of A, B, C, D real numbers. Of course, you could take this and rewrite this as what? It's like a 2 by 2 complex matrix with you got a Z, you got minus W, and you got W bar down here, and you got Z conjugate up here. So this is a representation of a quaternion as a 2 by 2 complex matrix, right? Where have we seen that before? I do not know. I'm not sure. I will talk about quaternions when given a chance, though. So it could be anywhere. Calculus 3. Most inappropriately. Number theory, I've managed to talk about quaternions for a day or two, yeah. Actually, about a week. I think I spent about a week in quaternions and number theory, that's true. You got me there.
I mean, that was actually the book.
I mean, I gave a visiting lecture on number theory this semester. I managed to work in quaternions. So I'm gonna work quaternions in. That's, rest assured. I just think they're interesting. All right, so let's get to Maschke's theorem. I would encourage you to read the rest of the examples. I hope I've done enough in here that you have a shot at understanding the problems. But that actually is my underlying motivation for giving you homework in here, especially in this part of the course, is just so you can better appreciate the reading. I don't think my lectures in here are sufficient to really master this material or even get close to that. I just hope we can start to understand it, and I can recommend some books to read after this for representation theory, especially if you're interested in physics. I've recently found a very nice book on it I can share with you. All right, so this is the theorem. I got to look at the spelling. Every time I look at it, I'm like, what? Is that right? CH. That's a lot of consonants in a row. All right. So here's the thing. Let G be finite group. And F a field with the characteristic. What's the characteristic of a field, guys? Right, how many times do we need to add the number 1 to itself to get back 0? If at all, right? If it doesn't ever happen, the field is said to have characteristic 0, right? So in particular, this theorem applies to fields with characteristic 0, which is, okay, in truth, all I care about. But that's because I'm a bad mathematician. Let's hear, if V is any, that's very close-minded of me, isn't it? V is any FG module. All right. And U, a submodule of V. Then V has a submodule W. Has submodule and submodule W such that V is the direct sum of U and W. All right. In other words, every submodule is a direct sum and. Okay. So I think the proof is pretty easy to follow. So let's just kind of work through it. The starting idea is essentially something I did in linear algebra today. So we just covered the first isomorphism theorem. One of the first examples I give after the first isomorphism theorem is that if you have A plus B and you divide by B, you get A again, right? I mean, the quotient of the direct sum of A and B by B is isomorphic to A. And so that's kind of the idea behind the proof to start with here. But let me just sort of follow this. So they're like, okay, so what we want is to produce an FG module homomorphism pi from V to U. So goal, produce FG module homomorphism pi from V to U such that what? we want it to, he says, we want to be a projection onto U. We need two properties. We need that pi of U is U. So we need like U is fixed under this homomorphism. And we also want that pi, let's see, how does he write it? Pi of V is pi of V for all V and V. Pi of V. Okay. AKA pi squared is equal to pi. All right. So what happens if we have that? So suppose we could produce such an FG module homomorphism, right? Suppose we already done it. Then what would that give us? Then by the first isomorphism theorem, right? For modules, which is a thing, right? We would have that V mod what? V mod the kernel of pi is isomorphic to the image of pi, but this pi is clearly a surjection if it does that, right? So this would be isomorphic to U. But what's the kernel of pi? Well, 0 is in the kernel, yeah, but
That would be the only one.
well, actually, this is just a bit of name calling. And here's the thing that I was forgetting. Just let, an important word to notice, W equal to kernel pi. Then we have that V mod W, right, is isomorphic to U. And that implies what? I mean, the reason, and now here I think I'm using finite, I mean, we're going to have finite dimensional V here. So we've got a finite dimensional vector space mod a finite dimensional subspace is isomorphic to another subspace. It follows, you can prove this, that V is the direct sum. Well, maybe I'm missing a few details here, but V is equal to the direct sum of U and W. See if I'm, let's see here. Well, actually, he doesn't say that. I mean, oh, he's actually working it out. Let's see here. Well, I mean, I guess I should just clarify. This at the moment is intuition. All right, we need to work that out. So let's see here. We need to show what? We need to show, given that I mean, suppose we've produced this FG module homomorphism, right? That satisfies this condition 1 and condition 2, okay? Suppose we've got all this. The second part of the proof is to produce the pi, okay? So I need to do what to show this? I mean, what does it take to show this? I need to show that two things, right? V is U plus W. And 2, I need that U intersect W is 0, right? So why can we see that V is U plus W given our construction here? He does the intersection first, actually. Okay, fine. It's just kind of silly. Let X be an element of V, right? And right. So what do you do here if you have nothing else to do? X is equal to, how about this, X minus pi X plus pi X, yeah? So if you look at this right here, right? What happens when we take pi of X minus pi X? Which is we're using property 2, right? So in other words, X minus pi X is in U, right? I'm sorry. Yes. I fail. Let's see here. The kernel of pi. Right. Now why I need, what else do I need? I need that the other piece is in U. How do I know that pi of X is in U? By number 1, right? So we took an arbitrary point in V, and by this one.
But isn't it also just called the fact that pi maps for
Yeah, I thought I wrote that down right. Maybe I'm supposed to have pi goes to the V there. That'd be more exciting, wouldn't it? No, this is V to U. So, anyway. But yes, just question of, it's kind of like, did the police solve it or the FBI solve it? I don't know. They're in jail anyway. Let's see here. So, so anyway, this much shows us that V is U plus W, right? Now let X, or let's let Z be an element of U intersect W. What's that tell us? Pi of Z is equal to? Now how do you get that? Pi of Z is Z. Oh, I'm sorry. See, because I guess I just gravitate to wanting to say that pi of Z is what? 0. Because it's in W. Oh, I guess it's just, right. So this is from the U, this is from the W, and so therefore U intersect W is 0. Okay. All right. I didn't do it very fast, but I hope I got the point across. If we can construct such a modular homomorphism, then we have shown that U has a direct summand W, which is formed by the kernel of the modular homomorphism. Well, that's interesting. Okay, so if you don't mind, I'm going to erase this. You okay, Cooper? Okay. Okay, so what he says since U is a subspace, it has a vector space direct sum complement W naught in V. All right, so assume the conditions of the theorem, and observe that V is equal to U direct sum W naught by the vectors, again, this is the vectors, just vector space. So complement W naught in V. I mean, how would you construct such a thing? It's pretty simple. You just take a basis for V, right? You take a basis for V, which is formed by taking a basis for U, which is a subspace here, right? And then the rest of the basis, beyond the basis for U, will form, the span will form some space, and that space will be independent of U. That space is W naught, so we have a direct sum decomposition of the vector space, right? But this is more than that, right? Because here we're talking about an FG modular homomorphism, right? So the fact that it's a vector space direct, this is not enough. This is just the vector space part of it. All right, see, as he says, W naught need not be, he's like, trouble is, W naught need not be G stable. All right. In other words, it need not be an FG submodule. All right, so I'm not sure. I think what he's saying, I don't know if he's actually using this past this part or if he's just making a comment here at the moment. Let's just go on. We'll figure it out in a second. He says, let pi naught let pi naught from V to U, all right, be the vector space projection of V onto U associated with this direct sum decomposition. Actually is using it. All right, fine. Remember that means we can write pi of U plus W naught, right? And this would just be defined to be U. And that's a well-defined function because the representation is unique for that direct sum decomposition. So this is for all U and U and W naught and W naught. All right. So he says the key idea of the proof is to average pi naught over G to form an FG module projection for pi. So he says for each G in G, define G pi naught G inverse from V to U. So I think, partly what he's saying is that this W naught may not be the W we're looking for. The W we're looking for is going to appear as the kernel of the projection we're working on building. But we're using these direct sum, a given direct sum. I think roughly as he's speaking, the idea is to start with the direct sum decomposition of V and then to sort of adjust it for the group, for the FG module action until it's sort of corrected. Sort of like if you were looking for an orthogonal decomposition of a vector space, you might just take any old vector space like decomposition and then work on adjusting it until you finally get it like orthogonal. Something similar to that idea here, maybe. Just a thought. Anyway, so, this hasn't been defined yet. So here, by G pi naught G inverse of X, I guess, equals to what? Oh, he uses V. I'll use V. Let me stop being weird. V G dot pi naught of G inverse dot V. So these things that are going on here, right? Remember that G dot V, this is what's going on here is the F, the FG module action of G on, on V, right? So we have this is given to us in the data because we're looking at an FG module. V is an FG module. It comes with this module action. This is taking group and acting on a vector, right? The inverse of the group element acting on a vector gives me another vector, right? And then pi naught does what? It gives me yet another vector, in fact, in U. And then that is a subset of V, so G dot that still makes sense because of the, again, FG module action of G on V. All right. So let's see here. So you can this is linear, that is linear, that is linear. So it's a composition of linear things, so this is linear. All right, good there. And he says, furthermore, if U is in the G-stable space U, so is G inverse U. I mean, I guess the other point here is that this is that U is a is U a stable subspace of this, right? In other words, if I take G pi naught G inverse of something in U, do I get back an element of U again? Let's see here. This V has what decomposition? It can be broken down like U plus W, right? Not. So I take G inverse dot this, right? I guess the point is that that's equal to, I mean, that itself is equal to, say, U prime plus W naught prime, where U prime is equal to G inverse dot U prime prime. Just to be an idiot about it. If you
Dot U prime prime, not just dot U.
Because I'm not entirely convinced that G inverse acting on the W naught wouldn't give you a piece which is in U again. Like I don't know that the original module action is U invariant. I think if U was given to not just be a submodule but like a fixed submodule under the action, that'd be more data, and the proof would simplify in that case. But I don't think that's given. So like I don't know that G inverse dot U is again in the submodule U. I mean, I don't know that G inverse W doesn't rotate into U sum. And if it does rotate into the U sum, that is going to go into the U prime. Then once I have that, I can rewrite this as G inverse G U prime prime. It's kind of dumb, but and then this would, well, I'm sorry, that's a different U prime prime prime. I don't know. How do I know that? How do I know that what?
That U prime is G inverse of U prime prime.
I guess this argument right here, I can take U prime, right? And I can rewrite it as G inverse G U prime, right? I guess I don't know for sure that this is in U again, right? But that doesn't really matter because pi naught pi naught of U prime is what? It's U prime because U prime we're assuming is in U. And pi naught.
That U is G-stable.
We know that already?
Yeah, I think by the correspondence between submodules and
Because that's what I'm trying to prove at the moment. I'm trying to prove that G pi naught G inverse is U stable. But you're telling me pi naught is U stable? Is G stable? U is G stable.
I think that's what the correspondence.
U is G stable.
FG submodules are G stable subspace V. Yeah, so U is G stable.
Oh, well then this is easier. Sorry. I'm an idiot. You already knew that. Let's see here. All right, let me stop trying to reinvent the wheel here then. Apparently that's what I'm doing. I've lost track of what we know and what we don't know. My bad. So the point here is that this would be, U plus W naught, right? And then that is going to be G dot pi naught of G inverse dot U plus G inverse dot W naught. I guess I still don't know for sure that this, how do I know that doesn't go into U? Do I know that? Thing.
But your pi naught only maps to U.
But if it does go into U, if this is in U, right, then pi still maps it back out. The point is, as I think about it logically, it seems like there are two cases. It could be pi dot G inverse U, or it could be G dot G inverse U plus, G inverse W naught. But either case, I still just get back, well,
I don't think it really matters because, wait, what are we trying to show here?
that's a good question. I think I was trying to show that this actually maps into U.
Yeah, well,
Oh, that's obvious now.
pi naught maps to U. So G is pi naught.
Yeah. Actually, that's a very good question. What are we trying to show? I'm an idiot. All right, so anyway. Ah, son of a mother, this goat. Well, I guess I have to stop now. Sadness. Anyway, the averaging argument I will try to go over next class to start with. Basically, past this point, he does something very sneaky. He adds these things up over the group. Since it's a finite group, you can sum over all group elements. And by taking some sort of average of these things, by taking averages, by averaging these things over the group, he manages to construct this module homomorphism pi that satisfies the needed property. It's a really neat argument, which I have muddled the start of and wasted all our time. I'm sorry. Anyway, I'll shut up.